Hello everyone. Allow me to introduce myself. My name is George Tony. I'm a senior software engineer at LinkedIn. Today we are here to have a course about for programming fundamentals, recursion. In this course, we are going to talk about recursion. So there are a few things in the agenda. Why we need to learn recursion? What is recursion? And what are the fundamentals of recursion? And then we are going to compare loop and recursions. And last, we're going to talk about what happens inside a recursion. Why recursion? The recursion is been fundamental part of the computer programming. It's present in all computer programming languages. The benefit of the recursion is that it is powerful to break down complex problems, and it is been often asked in interview questions by large tech companies. When you look at where it's being used, it's used mostly in large problem solving like trees, graphs, linked lists, etc. These are really required in understanding higher programming concepts. Now we have said why recursion. Now let's go to what is recursion. A recursion is a function that solves a particular problem by calling itself, a copy of itself, and solving a smaller subproblem of the original problem. For example, in this video, I'm going to speak mostly about Fibonacci series, which is important mostly taught in colleges and schools, so it will be easier for you to understand. Example, a Fibonacci series of function f of n equals f of n minus 1 plus f of n minus 2. That's the basic concept of Fibonacci series, and we will be explaining every concept in this function, using this function. So now let's go to the fundamentals of recursion. A recursion has three laws. One, a base case must be present. Two, after each recursive call, the state of the function should move towards the base case. Third, a recursive function must call itself. That's how it's recursion. And for example, like I said, Fibonacci series, f of n equals f of n minus 1 plus f of n minus 2, where the base conditions are 2, f of 0 equal to 0, and f of 1 equals 1. Now let's look at the first law for this function. First law, the base case is f of 0 equal to 0 and f of 1 equal to 1. And the second law, where each case iteration, we should move towards the base case. The second law, f of 2 equals f of 1 plus f of 0, where we can see that in the representation, it moved towards 0 and 1. Now the third call, f of n equals f of n minus 1 and f of n minus 2. So we can see that the value of n change reduces itself so that it becomes more closer to 0 and it calls itself again. So now I spoke about the recursive function for Fibonacci series. Now let's do a comparison for loop with a recursion. So in the screenshot I have attached, I have given both the Fibonacci series calculation using recursive function as well as the loop. In the above picture, you can see that def f of n equals n less than or equal to 1, the return else case, then a is set to 0 and b is set to 1, and we are iterating over the range n plus 1 and calculating the next value, temp is equal to a plus 1, and swapping the values and returning a. And this returns the Fibonacci series in a loop iterative manner. It is complex to understand when you look at it at the first glance. While when we look at the recursion, the function is just like a pseudocode, where def of f of n equal to n less than or equal to n 1, return 1, else return f of n minus 1 plus f of fib of n minus 2, and that's it. It's over. The main thing difference between these two comparisons is that writing a recursive function is often more readable, and this is more evident when you look at the solutions using graph traversals, tree traversals, etc., where entire code can be written in as much less code lines, while the entire looping iteration can take a lot of time and make it more difficult to understand for another one. And another thing you can find in looping method is you will be using stacks and loops, queues for doing the um, storing variables in an iterative manner, while it's not present directly in the recursive calls. So now let's go through the internals, like what happens during a recursion call. When a recursion call happens, the entire stack trace where the function stores the static variables are put in a stack, and each recursive call updates the stack and added above. And when you reach the base condition, then each stack is popped back, and that's how the recursion is solved. For example, if you check at the loop, if your one is the factorial one, where if you check for factorial of 3, it calls the factorial of 2, and it in turn calls the factorial of 1. That's shown here, and returns factorial 1 returns 1, factorial 2 1 into 2 2, then factorial of 3 is 3 into factorial of 2, that's 6. And similarly, if you check at the same stack trace of Fibonacci series of 3, the fib3 calls fib2 and fib1, which in turns calls fib2 calls fib1 and fib0, where fib1 returns 1, and subsequently 1 plus 1 plus returns 2, and 2 plus 1 gives 3. That's how the stack trace of Fibonacci series work.